All right, so we will go ahead and get started, and as people trickle in, we have plenty of speakers, so lots of good things to listen to. So, on behalf of RPI, congratulations on your acceptance, and we're happy to have you join us for our graduate research showcase. So we have 10 students here that are current PhD students at RPI that are going to share just, a little 5-minute synopsis of their research so that you can get exposed to some of the work that we're doing here. Already know one. There we go. So we have 6 core research areas at RPI, and you'll see them listed here. So we have 2 speakers from each, with the exception of computer system design. Unfortunately, they had a conflict, so their group wasn't able to make it today. But you can look on our website, and it will give you, under each research area, a list of the professors that work in that area and connections to research opportunities that they have and the work that they're working on. So we're just going to go ahead and get started unless there's anything I missed, grad council guys.
Nope.
Nothing? All right. So we're going to go through each of the research areas and just listen to presentations, and feel free to ask questions in the chat box, and we can try to answer them as we go, but we have a lot of speakers and a little time, so we're going to try to keep the pace quick. So we're going to go ahead and start with the information science and systems area, and that's Brock.
So welcome everyone. I am Burak Varıcı and I work with Dr. Ali Tajar. My research is broadly on causal inference from graphical models. And today I will talk about the type of problems that I study without being too technical. So firstly, what are causal graphs? Basically, they are the directed graphs which represent the causal knowledge. In the example that I put in the right, for instance, each of the smoking, birth weight, birth defect, and child mortality nodes, they represent a random variable, and the directed edges among the nodes represent the cause-effect relationship from one random variable to another one. So given data from such a causal structure, the first thing to do is finding the underlying causal structure, because normally we just observe data or we experiment and get the experimental data without knowing exactly what is the underlying causal structure. And it refers to finding the existence and direction of these cause-effect relationships, of these directed edges, basically. And there are also different types of data needed if we want to exactly recover the graph. And the second type of questions relate to how to use this causal knowledge. For instance, suppose we have the whole graph and the whole relationship, then how can we use it to perform a treatment effect estimation or a prediction, or how to use it for sequential decision making in different tasks. And to answer these questions, we also need to think about what fully or partial information is needed, because in most cases, we don't have access to all the graph, but maybe just some partial observations. So the first concept about the first thing we need to know about these directed graphs is just from the observational data, we can only obtain a family of equivalent graphs. For instance, for the 2 little graphs I put on the bottom right, they have the same set of conditional independences, which means they can generate the same data distribution. And at this point, we introduce the interventions, which are the forced changes to a model, which modify the local causal mechanisms. For instance, by intervening on the red node in the intermediate, we can identify now from this interventional data, we will be able to identify whether the data belongs to the right graph or left graph. So my main research question, very broadly, is learning from observational and interventional data. So I will consider 2 problems. First, I want to estimate the intervention targets in causal graphs. The motivation is that in many experiments, targets are not fully known. For instance, when we inject some material to a cell, usually there is an on-target part of gene or DNA or some part of the cell that is intended to be modified. However, the off-target effects are really common. And from the after the experimental data is available, we would like to identify where exactly interventions happened. It has a standalone importance, especially in gene editing technologies or in more physical systems, such as in cloud systems. The fault localization can be taught as an intervention estimation problem, where the root causes of an error is an intervention in the system. The second benefit of finding intervention targets is actually improving the causal structure, because it allows us to orient more edges. And we call that, I said, there is a family of graphs from the observational data. But by learning these intervention targets, we can orient more edges and reduce the ambiguity about the underlying causal structure. The key challenges in this topic is mostly the first one is the computational complexity, which usually grows exponentially with the number of nodes in the system, or the restrictive assumptions and the lacking theoretical guarantees in some heuristic methods. So I aim to design and analyze scalable algorithms that estimate intervention targets from the causal graphical data. And we have published one paper in one setting, and another for a more general setting, we have a paper under review. My next and more recent problem is deciding where to intervene in causal graphs. So suppose we have n variables to intervene. Let's say we have n various injections or treatments to apply on a cell, and we want to find the best combination of them. So usually these are not additive and not even submodular, so we can have 2 to the n options. So we want to use the causal structure among them for a sequential design of experiments and reduce the required a priori knowledge about the model. Like with as small information as possible, we want to design the sequential experiments to find the best intervention. So this was just a brief recap. I hope you have an idea, and you can contact me offline if you have questions. Thank you.
Thank you, Barack. All right, next we have Sean.
Hello. Can everyone hear me? Oh, hello?
Yes,
Oh, okay.
yeah, we can hear you. Thanks.
Do I have control over this, or?
You don't, so I should say that to the speaker. Sorry. Just give me like a quick next.
Oh,
I don't know if
okay.
there's a way we can share.
It looks like I can request to control.
Okay, then
Uh,
there you go.
okay. All right, great. So my name is Sean McCoon, and I'll be presenting on behalf of Professor Birsen Yazici's group. I'll actually be talking mostly about my work, which is optimization methods for synthetic aperture radar imaging of ground-moving targets, but also give a brief overview of, our general lab work. Oh. All right, so just a little bit about me. I actually graduated from RPI back in 2018, and now I'm a fourth-year doctoral student working with Birsen Yazici. So I've had quite a few years here under my belt. Again, I'm a research assistant working on radar imaging, and I've had, the fortunate benefit of being able to intern down at the United States Naval Research Lab down in DC for the past 3 or 4 summers now. And actually a big part of our funding comes from these government agencies such as the NRL, the Air Force Research Lab, Office of Naval Research. So if that's something that interests you, it's definitely something that Professor Yazici pushes and encourages over the summers at least. So for our group, we're comprised right now of 3 students, Samia, myself, and Nazia, and we also have a postdoc, Barshan, who graduated from our lab a couple years ago. And what we do is we focus on wave-based imaging for imagery construction and target detection. And really we can really look at our work as both theoretical and the application side. So for theoretical, we focus on convergence guarantees, imaging system requirements, fundamental limits of optimization-based approaches. Meanwhile, on the application side, it's, on an algorithmic level, how can we implement stuff like moving target detection and automatic target detection? I work in synthetic aperture radar. So if you're unfamiliar, SAR, which I'll call it, uses an antenna mounted to a satellite or airplane, which is known as a platform, to illuminate a scene of interest via electromagnetic waves. So sort of some of the benefits over typical optical imaging is that it can be used in all types of weather, so day, night, rain, snow, um, and I guess, yeah, it can be used day or night. And over typical radar systems, we can increase resolution without the need of an actual large antenna, since we are synthetically creating that aperture using a platform. Now, under far field approximations, I think this reduces down to simply the radon transform and Fourier slice theorem. So if you're familiar with some of these fundamentals from like computer tomography or MRI, we share a lot of the same principles. And what I really wanted to point out was, we look at this data model, and what we're really interested in is the phase of this data model. So the term in this exponent. If you see here, this R, which I should have maybe defined, is the range from the scatter to the antenna. So if we know that the phase and we know the speed of light, we can directly calculate where the target is within the scene. So the interesting question really is what happens when either part of that phase is unknown or we don't have that phase at all, because a lot of measurement systems, real-life measurement systems, can only measure the amplitude. And that's something Samia and Nazia are working on, sort of this phaseless measurement case. So I guess they could speak more about it, but I focus on moving target detection. So just like an optical image, moving targets often present themselves as smears across the scene. And this is because we don't know the velocities of targets in general. So we have some unknowns in that phase component. And we can't really directly calculate the range to the scatterer. Now, conventionally, this is addressed through space-time processing techniques. However, this requires additional hardware and increases, acquisition complexity. But you can imagine this can be a big problem when we're talking about our platforms being something like an airplane or a satellite. This can get quite expensive. So what we want to do is look at, all right, how can we shift towards using additional hardware into sort of these optimization-based methods, especially as, our computers and stuff become faster and faster. And really, what I do is I look at, how can I exploit either the matrix properties of the received data or really the underlying structure of the received signal model itself to achieve this. And some things we're always considering is we're always looking to ease computational complexity. Look at recovery guarantees, exact recovery guarantees, look at how robust our approach is to both noise and outliers. And this is always sort of, all of these are trade-offs, right? Like, of course, we want something that's really computationally efficient, but it does have to solve the problem. So, some of the things I've looked at are on the right, like looking at robust principal component analysis, which is exploiting the matrix properties of the received signal model or the received data. But right now I'm looking at sort of how can I actually exploit the underlying signal structure using sort of this atomic norm minimization framework. I won't really get into the details of this, but if you're interested in looking at problems like these, yeah, our group is definitely a good fit. Finally, I just have, an example of moving target reconstruction. A lot of our work we do is simulation based. So, we simulate scenes ourselves, but here you can see a scene of interest where the targets in the red circles are moving targets and everything else is stationary. And typically, if you were to image scene like this, you would only be able to obtain the stationary scene. But using this RPCA method, we can actually, exploit that matrix, split the matrix up, and recover both the moving targets and stationary targets separately. Yeah, that's it. Oh, sorry. Yeah, thank you.
You're fine. Thanks, Sean.
If you have any questions, I don't know if I left my email anywhere, but I'm sure you can find it. Yep. Yeah, thanks.
Thank you.
Yep.
All right, so next we're going to move on to the communications and networking research area. So we have you, if you want to request to take control of the screen, you can.
Oh, I'm sorry. How should I do that?
Sean, how did you do it?
For me, I have something on the left. There's the little marker, and then there's oh, I can stop controlling. There's a thing that says ask to request control.
Okay, I see.
Yeah.
Okay,
And request for the.
yeah, can you approve him, Sean? Because now you have control over the screen.
Oh, let's see. I stopped controlling, so I'll.
Okay, cool. Thank you.
Yep.
All right, go ahead, you.
Okay. Oh, that's cool. Okay, my name is Yuval. Oh.
Should be able to go back one.
Go up. Okay. Haha, delayed. Okay, it's a problem of it's a similar problem about the project I'm going to talk about. It's about the delay. So my name is Yuval, and I'm a PhD student under the supervision of Professor Bazet. And in our group, we work on network problems. So the slides I'm going to present is about our current project, which is about a new transport layer protocol design for multiplayer VR application. So on the bottom left-hand side, we show an image, which is a player-controlled VR avatar that is conducting a needle decompression, which is emergency operation for patient who is suffering from pneumothorax. So it's a VR-based simulation platform that is going to train a medication team to communicate effectively, especially during emergencies. So there will be multiple VR controlled avatar in a simulated surgical room, and then suddenly something emergent happens, and all the medication team will need to quickly discuss what is going on, what need to do, and then treat the emergency. So we model such problem. So we focus on the network module design of such problem, and we solve the transmission latency and the network packet delivery jointly. We propose a new network protocol, which we call RCP, and the diagram, also the graph, discuss the performance architecture and the performance of such protocol. So not like maybe you have heard of TCP or UDP that either optimize only one metric. For example, TCP only optimize the transmission delivery rate, which is 100% delivery guarantee, or UDP that only minimize the transmission latency, where care nothing about the delivery. Our protocol jointly optimize both and seek a balance between them to achieve a good performance in order, specifically for VR applications. So the problem we model that as maybe you have heard of MDT, Markov decision problem, or semi-Markov decision problems, and we derive optimal policies and also upper bounds and lower bounds on the performance. So the diagram I showed in the middle of the slides is a semi-MDP diagram, which is going to model the transmission and retransmission process. And the plot in the bottom middle is achieved system utility. So our protocol is the green line, which is so the blue line is for UDP yellow or orange line is for ARQ, which is another extreme in the network protocol. You can see that the green line is almost always achieve the best performance over the 3 protocol. So yes, so that's about the network work we are working on. So in the future, we are going to test our protocol in a Unity-based simulation, and also engage in the real surgical doctors and nurses and anesthesiologists into that to do more real tests. And this work is also going to affect the current COVID protocol design, and also have some psychological research and experiences training. So that's about it. Thank you very much.
Thank you. All right. So next up we have Hassan.
Okay,
You should be able to go back one. I think it skips. There's like a delay. I'm not sure why.
So maybe Lauren, if you could take up the control and I can just say next slide, if that's okay.
That's fine with me. All right. Trying to click back to you here.
Okay, I've stopped.
Perfect.
So yeah.
All right.
And if you could go to a few, great. Okay, thank you.
You're
Okay,
welcome.
thanks, Lauren. So hello, everyone. I am Saeed Ahsanuza Naqvi, and I'm a PhD student working under the supervision of Professor Kaushik Kar. And today I will be summarizing my PhD research, which is titled Energy Efficient Operation of Thermostatically Controlled Loads in Grid Interactive Buildings. So building energy management is a complex domain that has multiple stakeholders, each of whom has their own objectives. These stakeholders include the building operations manager, who has various responsibilities such as the negotiation of grid service contracts and analyzing energy usage of the building. We also have the grid operator, who among other tasks transmits signals for enforcing grid service contracts. We also have the policymakers and environment protection bodies that are interested in promoting sustainable buildings. Building occupants are also stakeholders in this energy ecosystem, as they are interested in enhancing their comfort and reducing energy costs. My PhD research primarily aims to address the overlapping objectives of these stakeholders. Right. So my research basically has 3 different directions. The first direction of my research develops a scalable power control strategy for HVAC systems in demand response amenable buildings. We define demand response, or DR, amenable buildings as those that allow indoor temperatures to vary about a certain temperature set point within prescribed bounds. The power control strategy that we proposed ended up expressing the optimization framework for minimizing the weighted sum of energy costs and thermal discomfort in terms of a single vector of control variables, which was the power consumed for heating or cooling the indoor spaces. Now that significantly helped reduce the dimensionality of the problem and was therefore computationally more efficient. Through our work in this first direction, we have shown that for specific building thermal properties and pricing schemes, the achievable percentage financial savings with respect to a given baseline can be up to 19%. The second direction of my research involves using data-driven predictive control for indoor thermal management. Here we focus on developing control policies to cater for 2 thermal management scenarios in a physical test bed. So the first direction basically dealt with a more simulation-based scenario. Here we are actually dealing with the physical test bed, which is the smart conference room, which is located in CII in RPI. The first scenario that we look at in the second direction is we call it scenario A, and it involves achieving a desired temperature by a fixed deadline, we call it K, in an indoor space in preparation of, for example, a scheduled activity, which can be a work meeting. Now, upon the beginning of a scheduled activity, one of two situations may arise. Either none of the participants of the activity may have any temperature preference, following which a standard controller can basically step in to maintain the indoor temperature close to the one achieved at the end of the pre-cooling or preheating operation in scenario A. Or the other case could be that the individual occupants put forth a temperature preference, following which the HVAC elements within the physical test bed are engaged to meet these personalized temperature requirements. So as you can see in this image at the bottom, we end up achieving a range of temperatures within the same room in order to meet the temperature comfort requirements of the individual occupants. The third direction, which I'm currently working on, is basically involves simultaneously managing the indoor air quality and the temperature in a multi-unit building. In our work, we use the carbon dioxide concentration at any given time to be the metric for determining the indoor air quality. Now, the reason why this problem is interesting is that the maintenance of indoor air quality and indoor air temperature can often be seen as competing objectives. For example, during winters, drawing in fresh air from the outside can in turn reduce indoor temperatures, which would cause the HVAC system to do more work. We are currently working on developing an optimization framework that minimizes the energy consumption of the HVAC system that satisfies both the temperature requirements of the building occupants as well as the indoor air quality requirements. So this was the third direction. And I am done with my part. Thank you.
All right. Thank you. Great. All right. So next we have the control and autonomy core research area. So we're going to start with Alex.
Yeah. Hi, everyone. I'm Alex, and I'm going to present all about robots. So it's very exciting stuff. I've been here, well, I mean, I've also been here for undergrad, but I've been doing PhD studies for 3 years. And over those 3 years, I've been doing 3 different projects that, when you first look at them, might seem a little bit unrelated. But when you go down into the very deep math that's involved, they're actually very, very closely related. So I'll start first with all the way on the left, this robotic deep rolling. For this, we worked with the company UTRC and with the ARM, which is a big consortium of lots of companies and schools that help work together to bring interesting research into our lab. And basically what this deep rolling process is, it involves applying a very high force onto a metal part, either aluminum or titanium. And by rolling on this metal with very high strength, you deform the surface of the metal. And this builds up residual compressive stress that helps strengthen the whole part. And classically, this has been done with CNC machines. But the problem is that CNC machines are small and they're very expensive compared to robots, which might be surprising to some people. So basically the goal here is, can we do the same process on a robot? And this is not very easy. And the most important part of this is the robot is flexible. So in order to build this process, you have to figure out the model of, if you apply a certain amount of force on the robot, how much does the robot move? So, we're applying very high loads to this metal piece that you see on the left, 1,000 to 2,000 newtons. And basically, to get the robot to apply the force, we're basically commanding the robot to go inside the metal part. So it's a very complicated process. But we were very successful. We're still working on this here and there, and everyone at UTRC and ARM are very happy. And we invented a lot of new math to help solve this problem. And of course, we can apply this to other things like grinding and other mechanical processes. So that was robotic deep rolling. I'll move on to this multi-robot system project that we did. Again, this is with ARM. So, our lab works with a lot of real-world companies to solve real problems using math. And the company we worked with was Pavilion. And what they do is they make tents, and specifically tents with photovoltaic cells on them to make electricity. So this specific project was to help make rapidly deployable hospital tents for COVID. We actually got funding for this project from Congress specifically to help solve COVID. So what this project involved was having a fleet of multiple robots. In our case, we had 5 robots. And basically the goal is to help all the robots work together to help operators make these tents. We had 3 different types of robots. One of those types was the Orbots, which are homebrew robots that we built ourselves, so basically from scratch. And on the top in the middle right, you can see these 5 robots all working collaboratively to help 2 people do RF welding to connect 2 pieces of fabric together. And these pieces of fabric are really heavy, like hundreds of pounds once you connect it together, and they make really big tents. And if you don't have robots helping, you either need dozens of people all working together, either that or the people might get hurt because of how heavy it is. So this robot system worked really well. Everyone's really happy. And we can do lots of stuff, like on the bottom left in the middle, you can see 3 robots moving a cart. And this camera is pretty high up, so this is an 8-foot by 4-foot cart, really big cart, and the robots work collaboratively to help move it. I think one of the most interesting parts of this project is because the robots are covered by cloth half the time, you can't use cameras to localize the robots, so we devised a system where we use only radio waves through a technology called ultra-wideband to help localize these robots. And right after we finished the project, that's when Apple started using UWB in their Apple tags, if you heard about that. So it's exciting that we got into this technology pretty early. And the fun part is that we also designed a really easy to use, really cool graphic interface and a wireless pendant to control these robots. And we've been using that on other projects too. So definitely a really cool project. So now we'll move on to the robotic satellite refueling. And we're working on this with NASA Goddard. We've been working with them for a number of years now. Really exciting project. And the goal here is we have this vessel on the left, and this was fly up into space, and it has 2 robotic arms with 7 degrees of freedom. And the goal is to come up to an existing satellite while it's orbiting, and it'll latch onto the satellite, it'll link the 2 vessels together, and then it'll refuel and repair the satellite in orbit. So very complicated, very exciting. And there's a lot of work that goes into this. So what I've been working on is modeling all of the dynamics. Just like in the deep rolling project, there's flexible joints. And even more confusingly now, there's a floating base because, of course, we're in space. And there's so many problems to solve, and it's really interesting math. We've been working on predicting and eliminating the stick slip effect. And this is nonlinear optimization. It's very interesting. And it's really cool the math that goes behind it. We use something called the describing function method to help predict and eliminate the stick slip effect. Going further, we've been doing path planning and trajectory optimizations, where basically the path is just the points in space that we want to move, and the trajectory describes how we move through those points over time. And then finally, we've been working on creating algorithms to actually move the arm so it follows this trajectory. And this is really hard because the motors in these arms are very, very weak because they want to keep the robot as light as possible for space. And the mass of the arm is way less than the mass of the load that it's carrying. So it's really complicated, but the goal is to have the controller as simple as possible so that humans can still tune it and understand what's going on. And of course, like I said before, it's a 7-degree freedom arm, just like a human arm. And what this means is, you can hold your wrist in exactly the same place, but rotate your elbow around the line that goes between your shoulder and your wrist. So part of the problem is, how do we tell where the elbow goes as we move through space? And I've even invented a new way to help measure this angle that prevents sudden elbow movement. So that's really exciting, and I'm happy that I'm working on that, and hopefully I'll have a paper out soon. Yeah, so that's 3 things that I've worked on as part of Professor Wen's research group. We have lots of other research, but I've put links down at the bottom if you want to learn more about individual projects, and my email's up top if you want to email me to ask more. Thanks.
Thank you, Alex. All right, next we have Yunxi.
Hi, I'm Yunxi Wen. I'm a first-year PhD student working with Professor Julius. So do I get control of this, or?
You can request it from me if you want. Yes.
Okay, sure.
Perfect.
Yeah. Okay, good. It's not working. Okay, yeah, sure. So my research area is in control system, automation, robotics, and machine learning. And also get my undergrad from RPI and graduated last year. and now I'm working as a first year student, and now I just start working as RA this semester. So I'm working on 2 projects this semester. The first one is on robot motion optimization, and this is also collaborating with Professor John Wen and Professor Daniel Paternin. And the goal of this project is to track a complex geometric path with robot arms. For example, you can see from the upper right image, we can have one robot holding a part and another robot holding a tool, so that the tool can like travel on the surface of this object. And currently we are having 4 graduate students working in the group on different aspects. And my work in the group is mainly on machine learning and trajectory optimization. And so in general, we want to decompose a complex trajectory into primitives. Like since the primitives are like pre-calibrated for robots by the company. So the robots can like move more smooth and faster on those primitives. And now we are trying to use reinforcement learning techniques to learn a policy that can like decompose the trajectory into primitives that can give optimal robot motion. For example, we want the robot to move as fast as possible and also in a uniform speed, like when we're traveling along the surface of the part. And so we have like 3 kind of primitives here. For example, move L is a straight line, and move J is a straight line in the drawing space of the robot, and move C is a circular, and not like exactly circular, it can be an arc, a path. So we can decompose like a complex path like this into primitives of move L, move J, and move C. Yeah, the second project is called like temporal logic neural network. And this project we're collaborating with people from IBM research. And yeah, this temporal logic neural networks under the large area of neural symbolic learning and reasoning. And the main idea is for traditional neural network, it works well as a black box, but you don't know what's going on inside, and you also don't know like what exactly function is approximating. So we are trying to replace the neurons in the neural networks using logical operators like conjunction, disjunction, something like that. And we can learn with this like logical neural network, we can learn logical formula that can describe your data or behavior of agent. And this technique, a lot of temporal logic techniques are also used in model checking and time series classification. So here it's not very precise to say it can be used in neural network verification, but it's also like widely used in control cases. And the previous previous work from our group shows that given a formula template, you can learn the importance of each timestamp. So basically, you can identify you have time series data. You can identify like which point is more important, and you can make decision based on those important points and ignore the unimportant data. And my current work is on temporal logic formula structure learning. So basically, it's like give you a larger search space and flexibility of choosing your formula, and you can basically learn any kind of formula structure. Yeah, and yeah, I think this concludes my research. And if you are interested in control and machine learning and robotics, please feel free to contact me or Professor Julius. Yeah, thank you.
Thank you. All right, so next up we have the energy and power systems research area. And we have Fernando. If you want to request control, go for it.
Okay, so my research is related to modeling, more specifically, multi-domain modeling of microgrids. So for those that don't know, microgrids are electrical systems, and it's basically a smaller version of the big transmission line. So it's more related to small cities or small regions of the bigger part of the electrical grid. And so first, let me just discuss a little bit what is modeling per se. So I like to think that modeling is the act of telling the story of the physical system through mathematical equations. So everything that is natural, everything that we create, every physical creation, you can think about it and you can model it through a set of differential algebraic equations. So we try to understand and represent reality through a set of differential algebraic equations that describe how each component acts and how they interact with each other throughout time. So this is an example, this picture is an example of a modern electrical grid. So we have all sorts of different components, and it can have thousands of components, each individual load within a house, the transmission lines, the substations, the generation, everything is, let's assume it to be our biggest macro view of our system, right? And I also like to think that modeling is like music. So for instance, symphony orchestrated music, when perfectly performed, has around 100 musicians. So think about it as having 100 components to the system that are playing in sync. So the same way that a orchestra has to play the music, everybody has their role. An electrical power system also, there are individual components, and each component plays a different role. So the idea is that these 100 musicians that are playing in sync, and thus they are recreating the story that the composer created. Okay. So each component on the left side, each component can be modeled through a set of equations. And if you think about the musicians, each musician has its own music sheet. So it's very important that each component or each musician knows their role, and having erroneous models of the components can lead to false results. The same way as thinking about music, playing erroneously throughout wrong tempo, wrong notes, even playing the wrong music sheet impacts the entire experience. And there will always be a better way of modeling your component. So you can think of, you generated a model of something that exists in reality. And in fact, that model is pretty good, but it can always be improved. There's always more information. There's always better models that can be created. And on the music side, there will always be a better way of playing the music. So musicians practice roughly 8 hours a day for decades in order to sharpen their technical skills. So I like to think about modeling, thinking about music in the same way. So how do I deal with this research roadmap related to microgrid modeling? So the first part is I had to model the necessary microgrid components using Modelica modeling language. So for those that don't know what Modelica is designed to provide object-oriented component-based modeling of complex cyber-physical systems. So it's a modeling programming language where you describe the models through algebraic differential equations, and then you create the interface, and then you can emulate and simulate multi-domain energy systems within one software only. So based on the models that I've created, I wrote 2 papers. The first one was published in a conference last year, and it's entitled The Modeling and Validation of Renewable Energy Sources in the OpenIPSL Modelica library. So this OpenIPSL Modelica library is the library that uses Modelica, that is utilized in our research group with Professor Luigi Vanfretti. And the second paper that I wrote and was actually accepted for the general meeting this year is a step forward in the models that I did on paper 1. So on paper 1, I went through some reports from different commercial software, and I recreated their models into our own library. The second one, I took models traditionally from books and from papers, and I transformed them to being multi-domain. So instead of representing the electrical or the mechanical and thermal side of, let's say, a thermal energy source throughout transfer functions, I actually created the models that utilize the equations that represent the physics of those different domains. So for instance, an example of the first paper, I created a PV model with irradiance. And this is something interesting because the original PV model that we can find in the manuals and in other commercial software, they were created specifically for you to run a simulation of 30 seconds. So in that case, you consider irradiance to be something short, and you consider your irradiance to be constant. But throughout the practicality of using Modelica, you can create and expand the models that already exist in the literature. And in my case, instead of putting only one power reference for 30 seconds, I simply created a radiance to power reference that you can run, that you can emulate a PV source, a PV panel for 24 hours, for 48 hours, the time that you want to simulate. And now the second one is the thermofluidic mechanical electrical model of a variable speed drive that drives a three-phase induction motor. So it's very interesting because everything that you see on the right after motor type 1, that is in the power system domain, that is only represented by a polynomial function that was fitted to emulate the mechanical torque, the mechanical aspect, and the mechanical side of the motor model. But we can remove that polynomial equation, and we can add the models that describe the pump, the inertia of the pump, the thermofluidic system, and in my case, also the controls, which is the volt-surge controller for the variable speed drive on the motor. Now, with the creation of these models, so there were a set of models that weren't implemented in OpenAPSL and that I had to implement so that we can use these components and model a microgrid in a multi-domain way. And now what we're doing is, now that we have the models and that we already implemented the models and we're slowly upgrading them, now what we're doing is we're creating a multi-domain microgrid test case for optimization and resiliency studies. So the middle image picture on the middle is an alpha version of the microgrid model that I created throughout the year, which uses all of the components that were implemented on the other papers. And this is very interesting because the microgrid model that I implemented, it actually came from an IEEE technical report where people actually use this microgrid template to study stability and resiliency and optimization. So now we have this model in our own open source library where everybody can play around with it. And the future steps would be to implement a model predictive control toolchain where we have our Modelica model, and we also implement the controls through Optimica, which is a Modelica specific optimization scheme. Then you can use Casati to make the models double differentiable, and then you can apply collocation and then apply model predictive control. And the other aspect that we want to implement as well is to implement the controls through reinforcement learning. Yeah, and that's it. Thank you. If anybody has any questions or would like to contact, you can contact me or you can contact Professor Luigi Vanfretti. Thank you.
Thanks, Fernando. All right, next up we will have Eric. Okay, I think you have to click and let me back in. Okay.
Okay.
Okay, awesome, thanks.
Hi, everyone. Can you hear me?
Yes.
Cool. Hi, I'm Eric Segerstrom. I am a second semester PhD student, and along with Fernando, I'm part of Professor Luigi Vanfretti's research group. As you probably gathered from Fernando's presentation, a large part of what we do is based on modeling and simulation of power systems, but there's also a fair amount of work that we do in data analytics. So I'll be presenting a little bit about a project that I started last summer as an intern with Dominion Energy, which is a energy transmission distribution company based out of Richmond, Virginia. Thanks. So the kind of motivation behind this project is that in power systems, you can sometimes have these oscillatory responses. And while there's some oscillations that are inherent as part of the interconnected power system, oscillations that appear and disappear can be problematic sometimes and can indicate problems with the system either locally or throughout the entire system, like equipment malfunction, system disturbances, or even something like poor operating conditions. And in the worst case, these oscillations can create a total or partial system collapse. So oscillation detection algorithms become fairly important. Now, traditional oscillation detection algorithms detect oscillations just by setting energy thresholds for different frequency bands that are preset. And while this is usually fine, that assumes that you're always going to have sort of the same baseline background energy, which again, that's usually fine. But in systems where you have some high energy density devices connected, like an electric arc furnace, which is an enormous machine that's melting down scrap metal to create steel. I think it's something on the order of like hundreds of megawatt hours, and it operates every 30 minutes or so. So you get these big, short spurts of high energy broadband noise. You can kind of see on the spectrogram on the right there, where you have those vertical striations, that is the arc furnace operating. And then you see horizontally, when you have those brighter lines, those are the oscillations that we're trying to detect. So when you have something like that, it increases the energy level of the entire system. And so while it's running, you can't detect these oscillations if you're having static thresholds set. So our goal was to create a method to detect oscillations even when you have this intermittent broadband noise. And the way we went about that was by applying sort of two methods there, spectral flatness and k-means clustering. Spectral flatness is just a ratio of a spectrum's geometric mean to its arithmetic mean. And essentially what that does is it quantifies how noise-like a signal is as opposed to how tone-like or close to a pure sinusoid it is. The closer to noise it is, the flatter the spectrum is, and the spectral flatness measure will be closer to 1. If it's closer to a pure sinusoid or a pure oscillation, your spectral flatness measure is going to be closer to 0. So if you wouldn't mind going to the next slide. This is sort of a simplified example of how this algorithm that we created works. First, the program calculates the power spectral density of a signal in 10-minute windows. And as you can see in the power spectral density plot on the left, you'll get these big peaks where you have oscillations at those frequencies. So by taking it in 10-minute windows, we then kind of collect all of the power spectral density peaks and cluster them to sort of decide what frequency bins to look into depending on where those peaks are appearing throughout the day. From there, we take those peaks and we apply a spectral flatness measure to it. And by clustering that, we can divide our spectral flatness throughout the day into where oscillations are likely present when the spectral flatness is relatively low, and where oscillations are likely not present where your spectral flatness is pretty high. So after doing that, we plot a spectrogram just to confirm, because it's pretty easy to visually see where oscillations are appearing on a spectrogram. And you can see by comparing those two graphs on the right, where you have those bright kind of lines moving across the spectrogram, it pretty roughly corresponds to your yellow spectral flatness, where spectral flatness is low. So in conclusion, we found that this is sort of a useful method to complement some traditional oscillation detection algorithms, because while it doesn't necessarily work as efficiently as traditional oscillation algorithms, it is effective at finding these oscillations when there is that intermittent noise. So yeah, that's that.
Thank you. All right, and we have the final core area that we're going to be focusing on today, which is electronics and photonics. So Yuhui, you're up first.
Okay, thank you, Noreen. And good afternoon, everyone. My name is Yu Hui, and it's really nice to be here and share my results with you. And now I'm a PhD student working with Professor Michael Shi. And today my topic is about the plasmonic teraFETs and its applications in high quality temperature sensing systems. So as we know, in the recent decades, the transistors are becoming smaller and smaller. So with the continuously downscaling of the transistor feature size, we have reached to a point where the transistor feature size becomes even smaller than the lattice or impurity scattering and the mean free path of the lattice or impurity scattering. So in this case, the traditional drift diffusion transport will become useless. So now we need to transfer to the system where we have the viscous or ballistic transport. And with this kind of transport, if you have a very high frequency excitation, a kind of collective electron wave called the plasma wave will be generated in the device. So the reason why we are focusing on the plasma wave is that the group velocity of the plasma wave is actually very high, which is even much higher than the saturation velocity of the electrons in the device. So with those advantages, we can break the frequency limit set to the traditional device and goes to the terahertz range. Okay, so now on the upper left, we show a traditional device structure of the terahertz. We have if we have incoming terahertz radiation shining onto the gate, and we have some asymmetry between the source and drain, so we can create some kind of oscillation of the electron density or plasma weight in the device. And then we have from source to drain, we can create a terahertz DC response. And according to our theory, this response is proportional to the power of the external radiation. And so in order to describe this kind of response, we need to abandon the previous drift diffusion model and transfer to the hydrodynamic equations. And in our recent works, so we are focusing on the innovations in the device structure, as well as the use of the novel materials on this device, so that we managed to increase the sensitivity of our device for like 10 times or even more, so that the device becomes more effective. I think with our endeavors and efforts in this area, we can create a better detector for the high frequency signals, and also those applications also pave ways to the future, like beyond 5G or 6G terahertz 6G communication system. And that's it. Thank you. And if you are interested in this area, you can check out those papers or contact me or even Professor Sher. That's it. Thank you.
Thanks, Yui. All right, and we have our final speaker, which is Saad.
Everyone, Lauren, should I take the control?
Yeah, that's totally fine. It's not letting me get over there. Oh, I think Yuhi still has control, so he'll have to approve it. Oh, just kidding. There we go.
Yeah, I have it now. Hello, everybody. I'm working with Dr. Musa and Gam in the physics department, but I'm an ECAC student here. My research focuses on free space optical communication using filamentation. So what is free space optical communication? So if we have a direct line of sight between the transmitter and receiver, we will see that, Lauren, my slides are stuck, I think. Oh no, it went through.
There's a delay, I think, but I see
Yeah.
it.
Yeah, sorry. Going back. So as we know that we can communicate from ground to satellite using radio frequency waves at the current moment. But using visible light waves, we can send much larger amounts of data, as the capacity of visible light wavelength electromagnetic radiation is much larger or wider compared to radio frequency waves. So, but in order for this to work properly, there's a big hindrance, which is the line of sight between Earth and ground. And usually, if you have cloudy days or you are surrounded by fog, this is unable. This causes the light to attenuate and spread out. So you will not get anything in your receiver. So what we are proposing is using something called optical Kerr effect, which if you have a really high-powered laser, a pulse laser, which operates with a pulse width in the femtosecond region, you can induce something called the Kerr effect, where your light beam focuses onto itself. This is a third-order nonlinear optical effect that occurs in any media if you have sufficient intensity going through that media. So for us, I think it was around 50 to 60 gigawatts per pulse of light. So when you have this and your beam focuses onto itself, at one point it becomes so intense it ionizes the air around it, and what you ultimately end up with is plasma. And the plasma sort of acts as an opposite reaction, causing the light to go out. But since you still have enough energy, the light wants to come back and converge, and a cascading cycle produces a really long uh, filament of plasma. Now, when you form the plasma, what happens is that you have shock waves, which ultimately dissipates the water droplets and particles around the filament. And using that line of sight, you can send a information signal through. So what we did in the lab was using the femtosecond beam, we focused it with the lens, and then we created something called a mirror coupler, which is basically a gold-coated mirror where we had at a specific angle, we drilled a hole so the light could travel through, and we formed a filament. And with the other beam, which is our laser, which is our information signal, we created something called an OAM beam, which for us was a Laguerre-Gaussian beam, which is circular in nature. So what we ultimately achieved was a circular or annular beam of light going around the channel going around the filament through the channel, and you're able to receive that signal at the other end. So here are some of the data that we collected. So using the method that we just talked about, using the spatial light modulator, we are able to change the properties, the spatial properties of the light beams that we're sending through the channel, right? So using the spatial light modulator, we were able to further modulate the signals using something we call spatial segmented division multiplexing. So what we did was we divided the ring into 4 bits, and we were able to modulate each quadrant or segment with a binary phase mask on top. And with that, we got 16 possible combinations, which we could send 4 bits of data through, and this would increase the capacity of our network even more. So this paper, these results are currently under peer review, and the preprint version is available on arXiv right now. If we are currently working on using this, we're currently working on characterizing the channel created by the filament, and hopefully we'll do some more computational work to do some work with different structured light beams, such as Gaussian arrays, Hermit Gaussian beams, and maybe even Gaussian beams as well. So if you have any questions, you can contact me. My information should be available online.
All right, thank you, Saad. And so, Barak, if you want to go ahead and stop the recording.